In this session, we are going to see the principal construction and working of a semiconductor laser. In a semiconductor laser, the semiconductor used is gallium arsenide. Therefore, it is also called as a gallium arsenide laser. What is the principle involved in the semiconductor laser? When a PN junction is forward biased, the conduction band electrons from the N-type combine with the valence band holes in the P-type near the depletion region, and the radiation is emitted in the form of photons. What is a PN junction? P is a P-type semiconductor and N is a N-type semiconductor. When these two semiconductors are brought together to form a junction, it is called as a PN junction. If P and N-type materials are heavily doped, it has large number of holes in the P-type and it has large number of electrons in the N-type. The PN junction is heavily doped and large current is made to flow through the junction, which creates a population inversion between the electron and holes, resulting to the stimulated emission. Population inversion is a state where number of atoms in the higher energy state are more when compared to the lower energy state. Here, electrons in the conduction band are at higher energy state and holes in the valence band are in the valence band. When compared to the valence band holes, the electrons are more in the conduction band. Therefore, population inversion has been achieved. Now, what is the material used here is gallium arsenide. So, gallium arsenide is a semiconductor laser. Next, construction. Gallium arsenide semiconductor consists of a heavily doped N and P sections. N is an N-type semiconductor, P is a P-type semiconductor. N is having excess of electrons and P is having excess of holes. Metallic contacts are provided to PN type in a heavily doped junction diode to apply the forward bias. If you look at the figure here, P and N type materials are brought together to form a PN junction which are heavily doped, and forward bias is applied to the PN junction. P type is connected, forward bias means P type is connected to positive of the terminal battery and N is connected to the negative of the battery, so it is called as a forward biasness. And two opposite faces perpendicular to the plane of junction are polished and made parallel to each other, which constitute a resonance cavity, and laser is obtained through the faces. Now here in this semiconductor laser, forward biasness causes the pumping mechanism, due to which depletion region is been decreased, and the active region, you can see in the figure, the junction is nothing but an active region, and opposite faces are perpendicular to the plane of junction, are polished and made parallel to each other, which constitute a resonant cavity, and laser is obtained through the faces. The first and foremost thing here is in a PN semiconductor diode, P and N type are forward biasness, which causes the pumping mechanism, and the active region is nothing but a junction region, and perpendicular to the plane of junction are acting like a cavity. So, the three requisites are being satisfied in this semiconductor laser. Now, we will see the working of a semiconductor laser. This is the energy band diagram where you can see here in an unbiased diode, the Fermi energy level P type is towards the left hand side and N type is towards the right hand side. In an unbiased diode, that is in the figure A, you can see the uppermost part of EV and the below EV is EF in the P type towards the left hand side. Upper part diagram, you can see the Fermi energy level is just below the EV. That means Fermi energy level is lying in the valence band of a P type semiconductor in an unbiased diode. Coming to the left hand side, it is an N type semiconductor. In an N type semiconductor, we have excess of holes in the conduction band. Therefore, we can assume that, or we can say that Fermi energy lies in the conduction band in an N type semiconductor. If you see here in an unbiased diode, Fermi energy level is uniformly distributed in an unbiased diode. That is the Fermi energy level, the dotted line which is in the same straight line in an unbiased diode. You can see here in the description here, the Fermi energy level is uniform throughout the unbiased diode in the figure 1. You can see the figure here. The Fermi energy level is uniformly spreaded in the valence band in the P type and in the conduction band in the N type. And in an unbiased diode, this is the energy level diagram. When the junction is forward biased, the energy level shifts as shown in the figure 2. If you look at the figure 2 here or figure B here, see here the energy levels has been changed here due to the forward biasness. You can see here forward biasness, the down part of the figure which is forward biasness, the energy levels have been shifted. That means EF in the N type of a forward biased diode is shifted up, and EV, that is Fermi energy in an N type, is been shifted up, and since it is forward biasness, depletion region has been decreased, and you can see the depletion region from the topmost part of the figure and the bottom part here, the depletion region is decreased and that region is become an active region. Coming to the p-type semiconductor, in the forward biasness, Fermi energy levels have been shifted, and you can see that electrons in the conduction band are at higher energy level. So population inversion has been achieved, and this population inversion has been achieved due to forward biasness of a diode. That means pumping is done by the forward biasness. Now if you look here, the width of the depletion region decreases due to injection of electrons and holes. So forward biasness is causing the pumping. Pumping means raising of atoms to a higher energy levels. So the electrons, more and more electrons are coming to the conduction band. Therefore, when current is increased and reaches a threshold value, population inversion is achieved in the depletion region, due to which large concentration of electrons in the conduction band and holes in the valence band. Pumping, as said, pumping is done by the forward biasness, which creates a population inversion. A narrow region where population inversion is achieved is called as an active region, where the lasing action takes place. If you look at the figure here, the active region, in the region active, where the depletion region has become an active region in a forward biasness, and in the active region you can see large number of atoms in the conduction band, large number of electrons in the conduction band, due to which the transition of electron from the conduction band to the lower energy band, the valence band, a radiation, the emission of photon is being as shown in the figure. The narrow region where population inversion is achieved is called as active region, and where the lasing action takes place. The photons traveling in the junction along the resonant cavity stimulate the recombination of electron and hole pairs, due to which intensity of coherent light beam builds up along the axis of the tube. See here, as this electron is jumping from the conduction band to the valence band, from higher energy to a lower energy, a photon is being given out. This stimulates the, in turn creates some more light due to the reflections, the laser cavities. Therefore, a large number of coherent beam has been built up along the axis of the cavity. Now, the semiconductor laser have a low power consumption. That means for a low, we need not have a high power, or we need not provide any high amount of energy to have a laser beam. It is a low power consumption. It is compact and highly efficient. But laser light is less monochromatic and more divergent compared to the other laser. We know that the characteristics of laser light is highly monochromatic, highly coherent, highly intensity, high focused, and least divergent. But if you see at the characteristics of the light given out by a semiconductor, it is less monochromatic. That means a range of frequencies or a wavelength you can see, and more divergent. It is more divergent, but as per the laser beam it should be less divergent, but the laser light given out by the semiconductor is little more divergent compared to the other laser. And also there are few disadvantages as well as advantages. What are the disadvantages here is, it can only be, the output given out is only pulsed mode of output. We cannot get a continuous output like a CO2 laser. And gallium arsenide laser produce a laser beam of wavelength 8400 angstroms. These are used in optical communication system, where we use fiber optical communication system. This semiconductor laser has been used. Semiconductor laser is used as a regular, you can see the semiconductor laser in our engineering physics laboratory, where they have an experiment to find out the wavelength of a given laser using diffraction method. Diffraction method. The laser exhibits the phenomena of diffraction because in the diffraction we use a coherent source of light so that we can see the diffraction pattern. Thereby every student who is studying in engineering will have to conduct this experiment, find out the wavelength of a given laser using diffraction method in the engineering physics laboratory. Also, it is extensively used as a reading device for compact disc players. CD is nothing but we can store the data in it. To read the data, the semiconductor laser has been used. This is the explanation of principal construction and working of a semiconductor laser. Along with that, we have seen few applications of semiconductor laser also. Thank you.